Good morning, everyone, and welcome to today's webinar. My name is Keira Proctor, and I'm the Managing Director of the A. Proctor Group Limited. Today, we're going to take a broad look at the physics and applications around construction membranes, what they are, where they are used, and how we can use their various physical properties to optimize the performance of our building envelopes. We've covered a lot of these topics over the course of last year, so this will hopefully serve as a good recap and review of this for those who've followed our series so far, and a great introduction for anyone that's just joining us for the first time today. We'll begin with a look at the common applications for membranes in modern methods of construction, and review some of the important aspects of building physics that apply in these situations. We'll then consider the types of membrane commonly used in these applications and the different performance characteristics and criteria we use for each. There are four primary applications for construction membranes. On the warm side of the building envelope, there are vapor control layers, membranes whose purpose is to prevent excessive moisture vapor from entering the building fabric, where it may lead to condensation problems. Vapor control layers will also block the passage of air if installed correctly. Vapor permeable or breather membranes are used on the cold side of the envelope. They provide secondary weather protection whilst remaining moisture neutral and not restricting the passage of vapor to the external environment. Roof underlays perform a similar secondary weather protection function to breather membranes, but not all underlays allow the passage of vapor. Impermeable underlays require moisture to be removed from the roof by ventilation. Vapor permeable underlays can reduce or eliminate this ventilation depending on their specific properties. Whether used in walls or roofs, vapor permeable underlays can be either airtight or air permeable, and we will discuss the effects of this later in the presentation. Finally, underneath the building, we have either damp-proof membranes or gas barriers. A simple DPM prevents moisture from the soil entering the building through the foundations, while more specialised gas barrier systems facilitate construction on contaminated land by preventing the ingress of subsoil gases into the building. How and where the membranes are incorporated into a construction and which combinations of physical properties are most beneficial depends on a variety of factors. The primary consideration is the building occupants. The purpose for which the building is intended and the level of occupancy establishes the baseline hydrothermal criteria for the design. A building which is densely occupied with high moisture levels, such as a gym or a swimming pool, will require a different package of moisture control measures than a building such as a warehouse, where there is a lot of air movement. Very low humidity. The temperature, humidity and moisture loads allow us to determine the vapor pressure associated with the specific application. Establishing a clear picture of the anticipated internal environmental conditions allows us to optimize the entire design from the building fabric to HVAC systems. This in turn can lead to reductions in both cost and complexity associated with overspecification. As well as the internal environment, we need to understand the external environmental conditions. Primarily, this means the weather and climate present where the building is located, but we can also include the soil conditions and any contamination present. Factors such as overshading and sheltering from geography or adjacent structures and solar gain should also be accounted for. With a complete understanding of the internal and external environmental conditions, we can then apply this knowledge to the design of the building itself. Each type and configuration of structure will behave differently, and membranes can be applied in different ways. Without considering the performance of the entire building envelope holistically, important interactions between different systems may be overlooked or not adequately accounted for. This is compounded by many variations between as-designed and as-built performance, or designs which do not accommodate the realities of installation processes and schedules. Modern design workflows and systems such as Building Information Modelling, or BIM, and digital twinning can go some way to simplifying the process, but any digital model is only as good as the information it is built on. So, in addition to a complete picture of the environmental conditions applied to the project, we also need to ensure we have a full set of physical data covering every part of the building envelope. As well as ensuring that the dataset is complete, we must also verify that the test data used is appropriate to the construction and conditions under construction. Once we have all the relevant data at our disposal, we can then move in to consider the lower level physics at work in the building envelope, the interactions of heat, air, and moisture. We've covered this in a lot of detail in previous webinars, which can all be viewed on our YouTube channel or on our Learning Hub at www.proctorgroup.com. So today we're going to quickly recap the main points and considerations. We'll use a simple timber frame wall as our example, but we'll consider what effects other construction methods have on these factors later in the presentation. When we think about the physics of heat and moisture in buildings, the start point of any consideration must be heat. The heat sources in the building envelope are a significant driver of air and moisture movement, and the energy associated with heating or cooling the insulated envelope represent the majority of energy use across the built environment in the UK. To account for the amount of heat loss through parts of a building, we use thermal transmittance of the element, or U value. Every part of the construction, from insulation to bricks, contributes to reducing heat loss. These contributions are measured using the thermal resistance, simply put, a measure of how much insulation each part provides. The thermal resistance is calculated using the thickness of the material and its thermal conductivity, which measure how easily heat flows through that particular material. The inverse of the sum of these thermal resistances gives us the U value, which is the rate at which heat passes through the element. So, the lower the U value, the better insulated the building. To this basic U value, we can then apply corrections to allow for fixings, air gaps, and ventilated spaces as necessary. Structural elements like studs or steelworks must also be accounted for, as these may not insulate as well as the layers which pass through. This additional heat flow, known as cold bridging, can lead not only to higher overall U values, but also to cold spots throughout the structure. We can also take the U values for each part of the building, walls, roofs, windows, and so on, and use that along with the element areas to build up a picture of the entire building's energy performance. In this whole building model, we also use psi values to incorporate the effects of junctions and floor zones, which can also increase localized heat losses. U values do not increase and decrease in a linear fashion. So, if we want to improve the U values in our buildings, we need to add exponentially more insulation thickness. This approach will soon become impractical as the thickness cannot be accommodated. Another factor that can affect the heat loss is air leakage. Anyone living in an older house will be familiar with drafts around doors and windows, and probably also familiar with how much warmer houses feel when these drafts are blocked. As the improvements that can be gained from insulation thickness diminish, air tightness becomes increasingly important. Whilst air leakage at doors and windows is easily identified and remedied, the building fabric itself can also allow air movement. Gaps and cracks, for example poorly fitted rigid insulation boards, can allow air to flow from heated to unheated spaces. This process is driven by both convection currents caused by heating the internal environment and by wind forces acting on the outside of the building. In addition to drawing heated air out and cold air in, this air leakage can also allow colder air to pass into the building fabric itself, allowing colder areas to develop not only at the surface, but also within the fabric of the element itself. Understanding the temperature distributions at both the internal surface and within the fabric is important when we come to consider the effects of moisture movement. This is particularly important in roofing applications, where air movement out with the heated envelope, for example in a cold roof, is an important component of minimizing moisture problems. If we also know the internal and external environmental conditions, we can use the thermal resistance and U value data to produce a temperature gradient throughout the construction. This allows us to predict what the temperature will be at any point within the construction. The environmental conditions can also give us a prediction of the dew point gradient in the construction. This is the temperature at which air loses its ability to retain water vapour and is affected by the thermal and vapour transmission properties of the various layers. These are known as the hydrothermal properties of the materials. If these two lines intersect, then the airborne moisture vapour will condense into liquid water at that point. This condensation can have a range of harmful effects, from mould growth to timber rot, so ensuring the element is designed to minimise or eliminate this condensation risk is critical. Guidance on avoiding moisture problems in buildings is detailed in BS 5250, the Code of Practice for Moisture Control in Buildings, which is referenced by the building regulations across the UK and Ireland. One solution provided in BS 5250 is to provide ventilation, ensuring moisture-laden air is removed before it can condense, and this can be considered the traditional approach in most cases. Today, though, it is not always necessary thanks to advances in both building materials and assessments. Vapour-permeable construction membranes and vapour control layers can allow designers to effectively manage heat and moisture to optimise dew points and temperature gradients, while air-permeable roofing membranes can permit airflow without complex ventilation openings. When using such approaches, it's important that a robust assessment method is in place to verify the design approach taken will be effective. BS 5250 gives two methods for determining the condensation risk: a simple assessment known as the Glazer Method, and a more complex dynamic assessment. The Glazer Method, as detailed in EN 13877, provides a quick and simple overview of the moisture transfer characteristics. But the trade-off for this simplicity is that it ignores the effects of more complex factors. It also considers moisture accumulations over a simple annual cycle, potentially leading to long-term issues being missed. To fully account for these additional factors, which also include the effects of external moisture sources and the capacity of material to store and release moisture, a more complex and dynamic approach is necessary. This dynamic assessment is detailed in EN 15026 and necessitates a higher degree of assessor training, alongside a more detailed dataset for both the building and the material used. BS 5250 details when each type of assessment is considered acceptable, but a dynamic calculation incorporating weather effects will always provide a more accurate assessment and may allow optimizations that could not adequately be assessed using the Glazer method. So let's take a look at how the various modern methods of construction affect some of these physical factors. By moving more and more processes off sites and into controlled factory conditions, such methods allow far more precise control of manufacturing tolerances and open up a range of possibilities for optimizing designs. A key principle underpinning modern construction is design for manufacturing and assembly, where the benefits of an understanding of the construction processes can allow the design to be tailored to work within these specific construction parameters. In this type of process, construction membranes of all types have an important role to play as part of a comprehensively engineered solution. The original modern method of construction is the open panel timber frame, where the structural timber frame panels are manufactured off-site and transported to site for erection and finishing. These panels typically comprise load-bearing timber studs with external sheathing boards, and in most cases an external breather membrane to provide temporary weather protection during transportation and erection. In this type of construction, the majority of additional processes such as fitting insulation, services and additional construction membranes such as vapour control layers happens on-site. This still delivers a wind and watertight envelope very quickly compared to traditional brick and block construction, but fitting insulation and services can still take significant time and require a lot of personnel on-site. An evolution of the open panel method, closed panel timber frame moves the insulation fitting into the factory, with additional sheathing internally to protect the insulation. While removing the need to fit insulation on site will save some time, the more important benefit is the quality of insulation installation. In this type of panel, gaps around insulation boards can be minimised and sealed, or expanding foam insulation types used to ensure the panels are inherently airtight. Building services are still typically fitted on site, but usually this occurs in a service void, making maintaining airtightness a little easier as less service runs need to penetrate the air barrier layers. Both of these types of panels share a common downside, in that the studwork and top and bottom runners of the structural frame penetrate the insulation layers. This means there is a significant degree of cold bridging present that we must account for and counteract, for example by adding an additional continuous layer of insulation over the frame. This cold bridging can be avoided by using a structural insulated panel or SIP system, where a rigid insulation core is sandwiched between outer layers of structural timber. This creates a strong and adaptable composite panel. Removing the timber stud-work from the panels provides a significant boost to the thermal performance. For example, a 140mm thick insulated panel can achieve a U value below 0.2, while the same thickness of insulation between studs will only achieve 0.3. As well as improving the panel U values, junctions between panels and at floors and corners are far better insulated, providing psi values and giving a more uniform internal temperature distribution. This thermal performance makes SIP systems a great choice for projects where energy efficiency is a primary concern. It's also relatively easy to achieve low rates of air leakage, but ensuring the panel joints are well sealed is critical. There are, however, two main downsides of this type of system. Firstly, the positions of windows, doors, and other elements must be fixed at the design stage, as the panels are specifically manufactured with later stage changes very difficult to accommodate. This necessitates close tolerances for foundations and other processes, as even minor on-site adjustments cannot be made on the fly, to the same extent as with traditional timber frame. SIP systems are also heavily reliant on blown insulation foams and heavily engineered timber products like OSB, which might not be a good fit for a more ecologically focused project. Cross-laminated timber or CLT systems use pre-prepared structural timber panels in a similar manner to SIP systems, with door and window locations fixed and the panels supplied and erected in a similar manner. The way the panels and the fabric insulation are manufactured and installed is significantly different, however. In a cross-laminated timber panel, softwood timber planks, typically 30 to 40 mm thick, are glued together to form solid panels. An odd number of layers are glued together at right angles to each other and bonded together under pressure to form solid structural timber panels, similar to large thick sheets of plywood. These panels can in theory be any size and shape, but in practice, manufacturing and transportation considerations tend to limit the size to around 3 meters by 16 meters. The alternating timber layers give the panels excellent structural properties, and being solid, joints can be made at any point. Because of this, panels can be optimized to fit more or less any strength or spanning requirements. Openings for doors and windows can be placed anywhere in the panels, but along with the general layout and structural design of the building, this must be fixed at the point of manufacture and cannot be changed later. In a CLT system, the insulation boards are typically placed on the external side of the structure, resulting in a similar build-up to the type of facade walls found in high-rise constructions. CLT systems also score very highly as regards to sustainability, with timber panels being fully recyclable and wastage being minimized. Each of these construction types result in a very different situation hydrothermally, with traditional timber frame having insulation bridged by the structure, while SIP and CLT constructions have unbridged insulation, but are placed in very different locations. The function of construction membranes is to ensure the properties and performance of each configuration can be balanced, adapted, and optimized to fit the project requirements. In each of these frame types, membranes are used slightly differently to complement the built-in strengths and advantages of the construction type, and we'll move on to take a look at that now. Setting aside gas barriers and other geomembranes, which we will cover in a separate webinar, we can classify most types of membrane according to these basic physical properties: vapor permeability, air permeability, thermal resistance, UV resistance exposure time, and reaction to fire. Acceptable performance criteria for each application based on these properties is detailed in the BS 5250 standard we mentioned earlier. BS 5250 is currently in consultation with a new draft expected pretty soon, but the various definitions have not altered all that much over the years. While these definitions give us a good starting point, there's a lot of specifics that are not included, and we'll take a look at some of those now. As we saw earlier, limiting the air leakage from the heated envelope of a building can have a significant effect on the overall energy performance. The level of allowable air leakage is arguably where the greatest gains can be made simply and for the least cost. Membranes to control air leakage are nothing new and have been part of a low-energy construction for a long time. However, where in a construction the air barrier is placed can have a big impact on its effectiveness and also its required performance. Historically, it has been most common to use vapour control layers as air barriers. A simple vapour control layer membrane, such as our Project 500 here, comprises outer layers of polyethylene and a core reinforcing mesh. Polyethylene-based membranes such as this are typically specified for low to medium risk applications, where the expected vapour pressure is lower. This would include most domestic housing applications, as well as offices, schools and commercial properties. If the vapour pressure is expected to be higher, such as in a swimming pool or a gym, one or more layers of aluminium foil can be added to increase the resistance. Vapour control layers are fitted on the warm side of the insulation and prevent moisture vapour reaching colder areas where it may condense into problematic liquid water, and the majority of VCLs will also work as air barriers. The main difficulty in using a VCL as an air barrier is ceiling penetrations. On the inside face of the wall, there are penetrations for all surfaces, switches, sockets, pipes and cables, as well as structural elements like floor zones and internal partitions. Sealing these up is by no means impossible, and closed panel, SIP and CLT systems that typically place services into a specific service void help mitigate this to an extent. It remains the case though that sealing all this takes time, and trades involved in later stages of fit-out may not be aware of the location or importance of the air barrier. Failure to meet the design stage air leakage rate can require expensive and complex remedial actions. A solution that reduces these potential failure points can allow the use of far lower air leakage rates more reliably. If we make our air barrier membrane vapour permeable instead, then we have some other options. Air barriers like our wrap-type membrane prevent air leakage whilst remaining open to the passage of moisture vapour. Wrap-tight has an airtight vapour-permeable film core with outer layers of spun-bond polypropylene and a vapour-permeable adhesive backing. The vapour-permeable adhesive allows for a faster and more durable installation to most common substrates, whilst making it as simple as possible to ensure a continuous airtight layer. The outer layers not only protect the film core from damage, but are also hydrophobic, allowing the membrane to provide temporary weather protection. This combination of air tightness, vapour permeability and weather protection mean that this type of membrane can be located more or less anywhere within the construction, even placing it between insulation layers if required. This is particularly useful in SIP or CLT constructions, where the membrane can protect the panels in transit. Then additional layers of thermal insulation can be added on-site without the risk of trapping moisture within these insulation layers. Being able to rely on achieving a low rate of air leakage can allow the level of fabric insulation to be substantially reduced. So, can we expand this external principle to other areas of the building envelope? In roofing, underlays are defined in BS 5250 as being type HR or high resistance or type LR, low resistance. The proposed revision of BS 5250 adds a third category, APLR or air permeable LR. We'll discuss APLR membranes shortly, but for now, let's focus on HR and LR. An HR underlay is very similar to a vapour control layer, in that it will not allow the passage of air, water or vapour. This makes HR underlays great at providing secondary weather protection, but because they cannot let vapour through, any moisture in the roof must be removed by ventilation. There's nothing wrong with this approach, but it can be complex to ensure the roof is properly ventilated, with good airflow throughout all parts of the roof. The openings themselves can also lead to problems with water ingress if not correctly specified and installed. The alternative to this is to use an LR underlay, which can permit vapour to pass through the underlay. The wrap-type membrane we discussed earlier can be used in this application, provided the insulation follows the pitch of the roof, in what is called a warm roof. When it is used on the walls and roofs of a building, this type of membrane can be wrapped around the eaves onto the walls and over the ridge to provide a continuous airtight layer. This provides a simple, durable and effective solution to ensure good control of both air and moisture movement. Where this type of membrane is less appropriate though is in what is known as a cold roof application, where there are large voids such as loft spaces between the insulation and the underlay. In this type of roof, it is recommended to provide a ventilation opening at the ridge, only to allow any buildup of vapour in the voids to escape. This solution is not ideal though, as apart from combining the higher cost of vapour-permeable membranes with the cost and complexity of ventilation systems, it can introduce a pressure drop in the roof, drawing more moisture from the internal space. This is particularly important in re-roofing an existing or historic property where replacing the ceiling may not be possible or desirable. Luckily though, another type of membrane allows us to engineer out that problem. In an air-open underlay, the AP-LR type membrane we mentioned earlier, the airtight film core of the LR membrane is replaced with a melt-blown fibre layer. These fibres are like a microscopic plate of spaghetti with very small pores and voids throughout. This microporous structure allows the passage of both air and vapour, but not liquid water. Combined with the hydrophobic outer layers, this gives us a membrane capable of providing temporary weather protection without compromising the movement of air and vapour. In our cold roof application, this means that there is a degree of air movement through those problematic large voids, which provides a boost to the transport of moisture vapour. This combination of air and vapour permeability makes the formation of condensation in the roof space practically impossible under most circumstances. This airflow allows us to remove any requirement to provide ventilation, and also means the ceiling does not require any specific measures to be taken. It might still be necessary to consider air leakage, but this flexibility gives designers alternative approaches to consider without any risk of roof space condensation. So, we can see from these examples the importance of considering what balance of air and vapour transmission properties are appropriate for a given project. Although air and vapour movement are the most common applications for membranes, other properties can also have a big impact on building performance. The next type of commonly used construction membrane is the reflective membrane. These can be either vapour-tight or vapour-permeable, but have in common a reflective surface, typically comprising either a layer of aluminium foil or an aluminium coating. This reflective surface alters a property called the surface emissivity of the material, which affects the ability of the membrane to either absorb or emit radiant heat. When used next to an airspace in a construction, this has the same effect as adding insulation. So, this performance is usually quantified by way of a thermal resistance or R value. While the R values associated with reflective membranes are typically quite low compared to insulation boards, they require no additional thickness to be added. This makes reflective membranes a great option where only a minor upgrade to performance is required. For example, as a trade-off to performance against glazing, but any big change to the overbuild-up is undesirable. In our example here, our base structural insulated panel gives us a wall U value of 0.2. If we add a reflective breather membrane to the outside, this will drop to 0.17, and adding a reflective vapour control layer will take it down to 0.16. Another important membrane property to consider is how it reacts to fire, determined by a single burning item test and classified according to EN 13501. This method exposes the membrane to an ignition source and classifies the membrane according to the energy and heat released, as well as the production of smoke and flaming droplets. These effects are then combined into a simple classification. Although membranes rarely make a significant contribution to the development of a fire, some circumstances, such as high-rise residential buildings, require a membrane to be less reactive. The minimum standard for these applications is usually Class B1 S3 D0. Achieving a Class B rating does not, however, mean a membrane will not react to fire. Most such membranes will simply shrink away from the ignition source or reduce the amount of energy available to feed the fire, but some, such as our fire shield shown here, have a different reaction. Fire shield comprises a polypropylene core which is airtight and vapour permeable, over a spunbond carrier similar to many other membranes. Where it differs is the presence of a specialist graphite-based outer layer which reacts to fire in a similar manner to intumescent coatings, frothing up to protect the layers underneath. While this reaction prevents the membrane achieving Class A rating, when compared side by side to another Class B rated material, the difference in reaction is striking. It's therefore important to look beyond the simple rating to consider the full scope of a material's performance and that of the system and installation as a whole. Particularly when considering vapor-permeable membranes, enhancing the fire performance beyond Class B can impact the vapor permeability, so it's critical to ensure the performance is up to the required specification. For vapor control layers, this is less of an issue. Membranes such as our ProCheck A2 VCL use a combination of aluminium and glass fibres to deliver high resistance to vapor and low emissivity surface, while substantially limiting the reaction to fire. This composition also makes such membranes extremely durable and resistant to tearing and other damages. The final type of membrane to consider is the variable resistance vapor control layer. This type of membrane is comprised of layers of specialist films which can vary their properties in response to different environmental factors. Membranes like our ProCheck Adapt have higher vapor resistance in the winter months when condensation risks are at their highest, but can open up to allow greater transmission of moisture vapor in summer. In this way, such membranes can limit the ingress of moisture vapor when needed, but can facilitate the inward drying of the construction when conditions are more favourable. So, that concludes our presentation for today, and we'll now move on to the Q&A session. Good morning, everyone. Welcome to our second webinar of 2021. Thank you very much for attending, and I hope everyone is doing really well. I'm glad you could make it today. For those of you that have attended before, as you know, we will stay and answer all the questions that are asked, so as long as it takes. So please feel free to either ask them here on YouTube, email us at webinar@proctorgroup.com, or direct message us on Twitter. After the webinar, if you would like to request, a product sample pack, a meeting with one of our technical staff, discuss a particular project or anything that was either in this webinar, prior webinars, or anything at all, you can do that and contact us online via our webinar app page and through the various mechanisms that you can find on our website. Personalised CPD certification you will also find on that webinar page, and I believe at the moment you can still register for today's webinar, which will mean that you will receive a replay. So if you've joined us from a different platform such as LinkedIn, then you can still register now and you'll get a replay of the video which you can circulate to colleagues and whoever you like. Date for the diary, our next webinar will be in 2 weeks. So quite a specialised topic. It's on Friday the 12th of February at 10 a.m. The topic is protection of buildings on brownfield sites. We actually have a very, very special guest for the webinar in 2 weeks, which is Paul Colbeck, and he is the chairman of the British Verification Council. So we'll have the similar, educational webinar followed by a Q&A. However, Paul Colbeck will be joining us, so a very well-respected chap in the industry. So hopefully it'll be a good one. I'm looking forward to it. If you have registered, you will receive a follow-up email with all the links and a link to the replay. It really helps us if you can give us a thumbs up or subscribe to our YouTube channel, and that also means that you will be made aware as and when we share new content on YouTube, which is something that we're doing a lot more of. We have quite a number of familiar faces on the panel this week, which is fantastic. Ian Fairnington is our Technical Director. Morning, Ian.
Good morning, everybody.
Good morning. Sue Menmuir is one of our long-standing technical advisors. Morning, Sue.
Morning.
Mark Lambourne is our Business Development Manager for high-rise and the modular sector.
Morning, all.
Hi, Mark. And Pamela Howitt is our Senior Technical Advisor, also based up in Blairgowrie. Morning, Pam.
Morning, everyone.
Good. So like everyone, we're all working from our home offices. However, we, all our staff are back at work, raring to go. So we're here to take your inquiries or assist you in any way we can. So I can already see quite a number of questions coming through. So I'm just going to start straight away. And as I say, bear with me. They come through in a few different platforms. I will get to them. So if you haven't asked yours in a timely manner, just hold on. I definitely will get to it as soon as we can. So Ian, if I can start with you, please. Sarah has asked, is a service cavity worth doing?
Yeah, a service cavity is always a very good thing to use if you've got space. So particularly in new build, when you're designing, before the design freeze or off-site construction, if you can allow for the service cavity, it is a really good option to use. It maintains the air tightness and the vapour resistance. If you put the vapour control layer in, then the service cavity, and allows the electricians and the plumbers to come in and put in their services in that service cavity, as the name suggests, without disturbing the vapour control layer. So there's no need for square holes for round pipes. They can do all their services in there, in that cavity, and then put the plasterboard in. So yeah, I would say always use it if you can. It also has thermal benefits if you use a reflective membrane along with it. And in certain circumstances, it can improve the acoustic performance as well. So yeah, if you can use it, please do.
Good. Okay, thanks, Ian. I like that. Square holes for round pipes. Good analogy. So Simon has asked, I wonder if you can take a couple of questions because they're kind of linked. So there's a question here from Simon and one from Jennifer. So Simon has asked, I'm in the early phase of designing my self-build and getting confused as to the benefits of vapor permeable over vapor-tight wall constructions. Can you help? And Jennifer also asked, is a variable diffusion membrane ideal for this? And I think she was talking about the roof structure at that point in the presentation. So if you could kind of take both of those and just try and demystify a little bit as Simon asks in his question.
Okay, I will try anyway. So I think this is mainly referring to the different types of insulation and membranes that you can use in the different types of construction. To put it, I suppose, relatively simply, a vapor permeable construction will look at using more natural materials, insulation such as mineral fibre, mineral wool, wood fibre, and obviously our space therm insulation, because they're more breathable materials. They'll look at the vapor movement in both directions. Membranes that work well with this will be obviously any of our vapor permeable membranes, which allow the vapor to pass through. Wrap-tight is also a really good option for this type of breathable construction, generally because it can quite often be used in sort of like low energy designs where there's other features such as maybe mechanical ventilation, for example. Internally, and this is probably where we would look at the ProCheck Adapt, which is the variable membrane, is ideal because again, this one is the ProCheck Adapt, as I said, is a variable membrane. So it changes its performance depending on the actual conditions. So it will become more vapor open or vapor tight as and when needed. And that will relate to roofs as well, for obviously for Jennifer's question. Vapor tight walls generally tend to use more the traditional types of membranes, such as our ProCheck 500, which is a reinforced polyethylene. We saw that earlier in the presentation. It doesn't, like it's vapor tight, it doesn't allow the vapor to pass through. Again, externally, any of our vapor permeable membranes will be suitable. And this is really only looking at the travel of vapor in one direction, whereas the vapor permeable option looks at travel both ways, moisture movement from outside to in as well as inside to out. So both options are obviously viable options. The best thing to do is obviously look at the construction as a whole, assess the condensation risk, make sure it's appropriate, and obviously that's where we come in. We can do that. We can do that for people using the Glazer method or the Buffet, depending on which one is the most suitable.
Yeah, I agree. So I think it's so important to look at the entire, what your entire, construction is trying to achieve across the whole envelope of the building rather than just one product or just one particular element. So it's a good point.
Exactly.
Pam, if I can come to you, please. Craig has has a traditional new build with screeded floors. However, he's used roof shield in a new build, which is this one, and he's noticing a lot of moisture on the underside of it and the roof space. Does he need to add vents? I think you can answer this one quite
yeah, easily. Yes. We have had a few isolated instances of this quite recently, which have predominantly been down to the construction phase and the weather. So all constructions, especially new builds, this one is, do have a degree of inherent moisture load in them. So depending on the type of building, so a SIPS panel or a factory applied panel that's protected, done undercover, is going to have a lot less water and moisture in it to start with, compared to a traditional build. You know, so you've got your brick and block, mortar, quite often plaster on the hard there, screeded floors for underfloor heating. All of that gives out a huge amount of constructional moisture that has to dry out and go somewhere. That drying out is dictated by the weather. I know that up here we're lucky if we've been above 0 for the last few weeks. This is actually positively balmy at about 3.5 degrees today. So we're experiencing very low temperatures, a lot of areas remaining around freezing. So combined with the rain, the snow, the storms that we've all been getting, there's a huge amount of moisture in that air outside around the country. And unfortunately also, the colder the air, the less able it is to hold moisture. So when it's very, very cold, it can only hold a small amount of moisture. If anybody wants to go look up psychrometric graphs, they can look that up. So when it's low temperatures, it tends to drop more moisture out of it because it just can't hold on to any more. So we've got, again, getting a combination of a lot of drying out moisture from the building, a lot of cold, wet air, not a lot of temperature, still air and things like that's not going to help as well. If it's a new build and the works are still going on, it's very unlikely that the central heating is on in there or there's any heating source in, so you're not going to get that vapor drive from inside to outside. So hold fire, don't panic. This is a phenomenon that is a rare phenomenon, but can occur during these winter months when it's wet and cold outside, a lot of moisture in the building. You need to get the heating on. You need to make sure things like your loft hatches, any penetration into lofts are sealed, your cavity walls are capped off properly. Make sure your trickle vents and your venting strategy is in place and working, and keep them open, don't seal them up. And get the heating on as quickly as possible at low temperatures. Don't try and be, you know, sort of like really blast it to dry out quickly, because that could be counterproductive. And, you know, let it dry out slowly. Traditional constructions can take months to dry out. You know, I mean, you know, they can be anything upwards of 6 months to properly fully dry out, depending on the constructions. And this time of year is not good drying out weather. So it's hang fire, hope for an early spring. And if anybody wants to read more, there's an excellent BBA bulletin, technical bulletin on it, with lots of hints and tips, and that goes over this. And it's a phenomenon with all vapor permeable underlays.
Thank you, Pam. That's really helpful. Yeah, and it's fair to say, obviously, the nature of that membrane will allow the drying out so much easier, especially roof
It's going to be so much faster than an airtight LR underlay in a cold roof type scenario. So yeah.
Good.
Well, I would say, sorry, Keira, great answer, Pam, and everything you've said is right. I think one of the things that you mentioned there was the closing off of the cavity is something that is quite often forgotten about. And that amount of moisture coming through, especially traditional brick and block construction, has a lot of moisture in it. And if you have the vapor drive will come through as it's drying out into that loft and can overload that loft. So it's a great point if you close off that cavity. And it's something that people should bear in mind when they're building, because it's so easy just to crack on and just forget about that small detail, which can make a big difference. So good answer.
Good point. And yeah, Pam, we're all hoping for an early spring, I think, this year. Everyone. And Pam, can I just ask you a question? Peter has asked as well, you show counterbatten on your roof illustrations. Is this a requirement of your product?
It depends on your construction. So the requirement for the counterbatten is only if you are unable to drape the roof shield into the top of your rafters. So if you can drape the membrane for sufficient drainage, you won't require a counterbatten. If you want to maximise the full depth of your rafter for insulation, or you're using a sarking board, like up here in Scotland, we quite often use the sarking boards, or you need it for structural, then Where there's no drainage underneath those horizontal tiling battens, you do need a counter batten. Now, that doesn't have to be massive. It can just be literally 12 millimetres to lift that batten up and allow drainage underneath to the gutter so you don't get ponding.
Okay, great. Thank you, Pam. Mark, I'm just going to dip back to an earlier question from Tom. The self-adhered external membrane seems to offer a number of advantages to off-site construction, but how would you deal with any remedial works if the membrane becomes damaged in transit or on site?
Right, okay. I guess really due to the robust nature of the membrane itself, both in terms of its weight and the fact that it's fully adhered back to the substrate, so whether it be a SIP or CLT panel, for example, then it's unlikely that the membrane is going to be either tear or easily damaged during transportation. If, however, repairs are required, then there's a couple of things you can do. The membrane is available in a tape format. So if you pre-applied the membrane in the factory, the guys can have a roll of this tape in the van when they're putting the panels together, etc. So you can use the membrane in a tape format, or you could use an offcut of the membrane itself. So just cut out a patch. So this provides a simple sort of patch repair. So you just remove the release liner and really looking for a 75mm lap all the way around where the penetration is. And what you would want to do then is protect the leading edge with liquid flashing. So the top edge, so any moisture that runs down can just go straight over the top of the liquid flashing and over the patch itself. The other approach really is if it's a smaller sort of penetration or a bit of damage, then you can use the wrap tight liquid flashing. So this is a gun grade sealant, which is supplied in a 600mm sausage foil. And you just literally put a bead of this sealant onto the membrane and then smooth it out with a spatula, and that will help provide a moisture and airtight seal. So really two approaches really.
Okay, brilliant. Thanks, Mark. Julie's asked one about the airtightness line via email. If I can just ask you another one, Mark.
Mm-hmm.
If a membrane is to provide an external airtightness line, how do you prevent air leakage at the wall, roof and floor junction or lap onto a DPM and gas membrane?
Right, okay. I'm not sure if they're available directly from the website, but certainly we've got a range of standard details. So these are typically for junctions and penetrations. So by all means, get in contact with us and we can forward those on. However, as every project is different, that it might require a sort of more considered approach and to address any sort of specific detailing with your particular project. So really, I guess from a design team point of view, it's great to get us involved at really an early stage in that design process. So at the present time, we're offering sort of meetings, team meetings or via Zoom to offer guidance, detailing. We can look at drawings and talk through those. The other alternative is to forward drawings in a DWG format. So these can be easily sort of marked up and color coded to indicate how we can achieve a simplified and robust external airtightness line. We're also doing sort of remotely at the moment for the contractors when products go out to site, virtual toolbox talks. So this really ensures that everyone following the basic principles and make sure that everyone really fully understands the importance of this install process. So there's lots of things that we can do whilst we're trapped in our respective four walls, working remotely. So as I say, by all means get in touch at an early stage and we can talk you through all of that.
Good, okay. Just a quick question to answer. Someone had asked, I've lost it now, do we have someone that they can contact in the London area? So I'll just answer that one quickly. Yes, we do. At the moment, we're only doing very essential site visits. However, we do have a number of people, technical specification, individuals and other national people. So you can either contact us at the moment at head office or in due course when things lift and you'll be able to see someone face to face. So yeah, we national coverage. We've got a relatively big sales team who can help you out with anything technically. Ian, I'm going to come to you on a question via email and ask you to answer one that has something in common with it. Again, it's come through on the YouTube feed from Ruth. So the original question from Josh, so thank you Josh for your question. I'm building with CLT, which membranes should be used and where? And Ruth has asked, does the external air barrier require a drainage cavity between the CLT and external insulation? So if you could kind of cover both of those, that would be great.
Yeah, I think the fact that we've had 2 questions just proves the point that CLT is growing in popularity in the UK.
Absolutely.
It's a nice, good construction. It has lots of advantages: sustainability, energy efficiency, good weight to strength ratio. So there's lots of good benefits of using it. Like any system, you have to be careful what you do with it from a moisture penetration and build programming. The most critical thing with CLT, or one of the most critical things with CLT, is the moisture generation and moisture management. During construction, the panels are sitting up there. It can be exposed. In the UK, we do experience rain occasionally, so there can be moisture in the CLT panel. So you need to protect that as best as you can. And we have a very good product in terms of Wrap-Tite and other options, but Wrap-Tite is particularly good for this on the outside of the CLT because it provides the weather protection to stop the moisture in the CLT panel, so it protects it. It provides vapor permeability so that the construction can breathe, and it provides an outside airtightness line. So the Wrap-Tite can be a really good construction in there. In terms of the build-up that Ruth mentioned, the build-up's important. Most of the CLT comes from Europe, and it requires external insulation. Now, in Europe, that external insulation tends to be a moisture open insulation, as opposed to a polyurethane that we're more commonly use in the UK. So that moisture open insulation, like a mineral fibre or a rock wool, is really quite important to keep the vapor permeability of that construction in place. So designed right, put that insulation on the outside, directly up against the Wrap-Tite, as I mentioned earlier. You don't need that drained cavity. The drained cavity can come on the outside between the external cladding and the insulation, rather than having an air cavity behind the insulation. If we had a drained cavity behind the insulation, that could create a degree of thermal bypass where you're actually losing the benefits of that insulation. So the construction would be a panel, Wrap-Tite, insulation, and then you could use a reflective membrane or just have a cavity and then the external cladding.
Brilliant. Thank you very much, Ian. And if I can come to one that I've had via email, Ian, just to give you a couple each at the same time. Paul has asked, should you build to regulation backstop values or strive to best practice passive light specification? What are the issues with either?
Really good question. And I have to use a terminology that the sales team give me a hard time for all the time. It's terminology that Pam's already used today, so well done, Pam. You're great in the technical team. And that answer is it depends. Building to the backstop regulations, in a school report, it's equivalent of a Class C. It's a pass, but you could do better. It means you have complied with what the government has asked you to do. And the building regulations are basically designed as a minimum. And sometimes people forget that. That is not, you've got to strive for the building regulations. What you've got to do is that is the minimum. And if you go further, then you're going to get a better build. So to do that, you could go to the strive for the best practice passive house type construction. Can be a lot better. So then you're getting to the A+ type construction. The reason it depends on your role in the building procedure. If you're building a house to make a profit, as some developers do, then that tends to be built to the bare minimum to comply. If you're going to build that house to live in, then the whole life cycle of energy efficiency comes into consideration, and the payback in that can be really important. So if you're going to live in that house, you want to make sure that the cost of running that house is going to be less. So the old adage of buy cheap, buy twice can be the case, that if you're actually living in it, you've done it to the requirements, well done, but you're just making it comply. Go for the A+, and you will get a better construction that you will ultimately benefit from.
Good. And Ian, questions come through just again to keep with you for a minute. Thomas has mentioned in reference to condensation issues at the moment regarding roof shields, which I think maybe we should clarify a little bit more, the difference between, moisture and condensation issues. But would you recommend a VCL at ceiling level to combat this? As I notice your literature states no requirement for a vapor control layer. So I think it's important you take this one in and provide a bit of clarification.
Yep, I can take that one. I mean, certainly the moisture issues that the Pam dealt with is really just during construction and during the drying out period. What we're saying is you don't need a vapor control layer because of the air permeability of the roof shield. It's a very low vapor resistance, so it's very vapor permeable, breathable, some people would call, and it's also has the added benefit of being air permeable.
Oh, the props, excellent. Love the props.
We have a demonstration here. I always keep this in my shelf above me, but I'm pumping into that, and you can see that there's a lot of air coming in through there. And that roof shield, that air permeability affords it so much more security from a condensation point of view during the life of the building. So you don't need that vapor control layer. Now, I had a 12-month fight with a BBA to put that statement into the BBA to say that a vapor control layer wasn't required. Now, that wasn't a 12-month fight on technical terms. I went down to Watford to see them, and I took a big bundle of tests that we'd done, research we'd done, and the point was made that it wasn't going to be a technical fight. It was going to be a political fight. What would the other manufacturers think? And I didn't care what the other membrane manufacturers think. If they had the same level of research, then they could have the same claims. What you tend to get now is claims that you can consider a vapor control layer, or you should consider it. Our BBA definitively says you don't need a vapor control layer. Now, that's not necessarily during the construction. So a VCL at ceiling level during construction, during the drying out period, won't make any difference. What we're talking about is the vapor permeability of the membrane during construction, and that doesn't need the vapor control layer.
And to be fair, not that I'm pulling on your age, but that was many years ago, this fight. This isn't something recent that Roof Shield has introduced. So, I mean, you're talking tried, tested. I mean, how many years, Ian, are we talking about the lifetime?
Yeah, I would say this fight has been going on. Well, our certificate came out in 1999. I had a bit more hair then, certainly. So, yeah, I mean, we're talking 20, 25 years ago that we were trying to teach the market that an air permeable membrane in the roof was good. Unfortunately, construction industry is such that they don't embrace new technology quite as quick as other industries. But we're a conservative lot. I think people have started to realise Roof Shield Special and the air permeability is different, and it's not just the same as other breather membranes.
Yeah, sure. I think that's what we try to identify when we're talking about the different types. Did you have something to add, Pam?
Yeah, I was just going to say something that I'm sure Ian would agree, I hope he would agree with, is that it's not so much the vapor control layer that's important, it's ensuring that ceiling is well sealed. So it's making sure your loft hatches are sealed and that you're not putting through things like recessed lighting without taking proper consideration. And it's really about controlling that rather than having that well sealed, which you should be doing regardless.
Good. Thank you, Pam, for that addition. A question here from, just coming back, so I'm missing a few on the feed, and there's quite a few more via email, so please bear with us. Ben has asked, on some barn conversions where they're being internally lined with a timber frame and a cavity, it's impractical to install a sarking board on the outside with a breather membrane. What can be done? Is that one for you, Pam? Sorry, I see you nodding.
Happy to do that. Yeah, it's a fair point. I mean, we quite often get people saying, I'm doing a barn conversion, I'm putting a timber frame up inside, I've got my membrane and my sheathing. In reality, that is a very difficult thing to do. It's either a case of trying to build a panel flat and getting it up and fixing it in. But it quite often in timber frame buildings, the purpose of that sheathing, that sarking board, is there for racking strength and structural integrity of the wall. Now, in a barn conversion, your existing wall is already your structural element, so the framing is potentially just there to hold your insulation. So I wouldn't be too worried about not using a sheathing board in that situation. Or the alternatives, if you needed that extra rigidity, use it on the inside and then just consider having an open frame at the other side. So again, it depends on, you know, the wall construction and any issues that might be there, but it's not necessarily needed to have it. Sometimes just offsetting that frame slightly is sufficient.
Okay, that's great. Thank you, Pam. Sue, Peter has asked, internal insulation to a 19th century building with solid masonry walls, something we see a lot of, are both vapor permeable and vapor open construction suitable? Would wrap type be appropriate on masonry inside face?
Yes, absolutely. Generally with these type of, you know, it's like historic solid wall constructions, they generally tend to be a more vapor permeable construction anyway. So you want to keep that and control that movement of moisture anyway. Wrap type will certainly provide air tightness as well, which is different obviously to the vapor permeability. But we do actually have a product called Wrap Therm, which can be used on the inside face of masonry constructions, which will provide the air tightness, the breathability, and it also uses our space therm insulation as well. So that is, again, another vapor permeable, breathable insulation material, which can also obviously help, depending on what they're doing inside, take away the cold bridge element of any internal structure that is going to be applied.
Perfect. And Sue, one we've had via email, this is about sarking. So what would the effect of using sheet sarking, i.e. plywood, over traditional softwood in roofing applications be?
Sorry, I've just collapsed here. Just give me a second. Yeah, so sorry, sheet plywood over...
Sorry, so what would the effect be of using sheet sarking, i.e. plywood, over traditional softwood?
Okay, so the main difference there is obviously the breathability aspect again, for the different types of sarking. Your traditional softwood sarking generally tends to be 150mm planks of timber, softwood timber, and you have natural gaps in between, around, you know, it's like 2mm, for example. And this is a permeable option. And as such, we can use this with our roof shield in non-ventilated warm roofs, cold roofs, and more complicated room in the roof designs. Your sheet sarking, such as plywood or potentially OSB, for example, they are less permeable materials. They're large sheets and they've got little gaps between them for that air movement. And as such, they are perfectly suitable in warm roof applications when using roof shield. The insulation would be placed tight up to the underside. And what that does is obviously moves the dew point out with the structure. So any condensation occurs safely out with the actual roof construction. Cold roofs, at the moment, you must provide ventilation if you're using this type of sarking board.
Okay, great. So that question was from Max via email, but I think you've also just answered Ryan's. So he'd asked, he'd said, I presume OSB or ply sarking is not simple to use a roof shield, so you've covered that. Traditional open jointed timber board system is the best solution. So I feel like you just covered that.
Yes.
Do you know, I love seeing the trends of the questions that come in as well, because they're all, sometimes we get 2 or 3 that are very similar. It's fantastic. Okay, we just coming back to another one that we had via email. Bear with me 1 second. Ian, if I can come to you, and then Mark, I'll come back to you for some other questions I've had. But Ian, Rob has asked, with the focus on closing the performance gap in the proposed changes to Part L, the advice around partial fill rigid insulation and cavity walls is to tape or lap the joints. Given that taping boards with a traditional aluminium tape has the potential to create a VCL in the wrong position, so excellent point. So on the cold side of the insulation, is there a vapor permeable tape available that would mitigate this?
Great question, Rob. Setting us up for a very good answer there. Yes, we do have a tape, funnily enough. We have the wrap type tape, which is vapor permeable, airtight, and water resistant. So, on the way to you, Rob. Thanks very much for that question. It's very true. So it raises a really good point. It's something that's been always irked me in the construction industry with the cavity wall construction. It makes a lot of sense to put a tape over the square edge joints, the butt joints, which could allow moisture to come through. But disappointingly, the foil tape was recommended. Now the foil tape, just exactly as Rob said, it's on the wrong side of the insulation. So therefore, when you get the vapor drive coming through those gaps in the insulation, it can't escape, and it can condense, particularly because it's a metal tape, in that area and create a build-up. Now, when I've asked in the past, does that not cause a problem? The answer I get back is it's never been, we've never had it reported to us of a problem. Well, yes, you wouldn't get it because it's built into the construction where you can't see it behind that foil tape. So it's very true. If you put a breathable membrane in there, vapor permeable, to be more precise, that is airtight, then that can allow that construction to breathe, and it's a great solution against the foil.
Good. Thank you very much, Ian. Okay, Mark, I hope you're prepared. I've got 2 or 3 via email and a couple on the YouTube feed for you. If I can just ask one we've had via email from Julie first, please. If a membrane is to provide an external air tightness line, how do you prevent air leakage at the wall, roof and floor junctions? I've already asked this one, so just ignore me. Yeah, I'm getting old. I'll come back to the next one. So Jeff has asked, are there wall membranes which provide higher levels of UV resistance for open jointed cladding systems, for example?
Yes, there are. And I guess with regards to UV degradation, you really need to look at either third-party accreditation or perhaps manufacturers' data sheets, and that will give you an indication or confirm the maximum exposure time for wall membranes. And in the case of open jointed facade or cladding systems, then obviously you're looking for that long-term UV resistance. That is going to be key. So we have a product called Facade Shield UV, which is a non-woven breathable membrane, and this is designed to ensure that the building fabric maintains both high level of water resistance, but also UV resistance. So for example, during the construction phase, the Facade Shield UV will offer UV protection, but fully exposed for up to 12 months. But once it's installed with the cladding in front of it, the open jointed cladding, then it will essentially last for the lifetime, certainly of that facade system, but the life of the building. So these open jointed cladding facade systems, they create a shadow gap detail. So the membrane is dark in colour, so you don't see a core blimey yellow or whatever it may be behind there, or a coloured membrane. And if you take the laps, then you get enhanced air tightness to the building as well. So the membrane is airtight, and you can take the laps as well as a tape that we provide. So depending also on the substrate, then there's it really achieve a class B S2D0. But as I say, that really depends on the substrate. So you know, please get in touch and we can talk you through that to let you know what that reaction to fire will be on your type of construction. And with regard to that open facade, we're really looking for the joints to be a maximum of 50 mil, and we're looking for coverage of that facade to be less than 50% of that whole area.
Okay, great. You just mentioned fire briefly there. Is there anything you want to add? Because Jennifer has asked, in relation to fire, where does fire resistance come into play for membranes, if it does at all, because she's not sure, used on these rain screens for buildings over 11 stories. Is there anything else you wanted to add to your comment there, Mark?
Yeah, well, with regard to reaction to fire, it's certainly a consideration, obviously, post-Grenfell, etc., and the unfortunate events there. So certainly it's one of the key things that people are looking at now, particularly on high-rise buildings above 18 metres. So you need to be aware of the type of membranes you're using, and also consider the reaction to fire testing. So if you look at the amendments within Part B, there is a regulation 7 which sort of states that provided your membrane is a class B, minimum S3D0, then you can use it on the construction above 18 metres. And certainly on these larger high-rise buildings, you'll tend to find that you have the sheathing board, so a calcium silicate or cement particle board, and then you'll apply, for example, our wrap-type membrane, which achieves a class B S1D0, and then you'll have something like the Rockwood Duo slab or the Knauf equivalent in front of that. And certainly to meet some of the U values these days, you know, that can be as much as 200 mil in front of the membrane as well. So if you consider within that construction, I guess you've got the cement particle board on one side, you've got the wrap type providing that air tightness, etc., and then you've got this non-combustible A1 insulation in front of it. But you certainly need to look at the membranes, not only in terms of fire performance, but also does that membrane actually meet BS 5250? So is it fully breathable? Is it suitable for the UK climatic conditions, etc.? And again, we can offer advice on that.
Okay, thank you, Mark. One last one from Jim, if I can just come to you again. Again, it's regarding the self-adhesive membrane. So are there substrates which may require a primer before applying a self-adhesive membrane and do mechanical fixings such as wall ties or the attachment of cladding systems, and will that affect your tightness?
Well, I think as with any self-adhered membrane, it's important that you prepare the substrate to achieve a good effective bond. So if it's a concrete frame building, then you might find that latents are present. So this is a dusty surface on the face of the concrete, and that can be easily removed by using a stiff brush. It's quite surprising actually the number of contractors that try and put a self-adhered membrane to a dusty surface. Well, all you're going to do there is adhere to the dust itself. So just very quickly brush that surface down with a hand brush or a yard brush. That will remove that dusty surface, and you've got a good bond there. When we're adhering to sort of sheathing boards or timber substrates, there's generally no issues. The only exception I would say is wood fibre board. So particularly around window openings where you've got that exposed edge detail of the boards. So in that case, you would need a primer, and there are products such as the Pavaprim to seal around those window openings, for example, and then you've got a good bond as you dress the self-adhered membrane through. In relation to mechanical fixings, I think really third-party testing, but also site experience confirms that we achieve very good air tightness results where you're putting fixings through, and that's really down to a number of factors. One is obviously it's a very heavy and robust membrane, it's 3 layers, and the fact that it's fully self-adhered back to the substrate offers really quite a good level of self-sealing around any fixings you're putting through. But I guess if you consider the type of fixings you're going to be using, whether it's a helping hand bracket or a rail system, as you're fixing that system back to the substrate, you're obviously applying pressure and compressing that membrane, and you're achieving a very good air and moisture tight seal. I guess further to that, what you could use is the wrap type liquid flashing. So you could put some of that on the back of the plate first, put that plate back, and then screw fix it through. Yeah, we've had some really good results in terms of air tightness, and not really found it to be an issue when you're putting fixings through.
Okay, thank you very much, Mark. Pam, if I can come to you. So there was a little bit of, we were trying to clarify. So Hassan Ahmed had asked, what are the benefits with sheet application as opposed to spray application? Now, when that question was asked, we were talking about the wrap-tight external self-adhered air barrier, and I think our techies have further clarified it, and he had said it's spray-applied membranes. So can you just maybe clarify what we know about, it's not something we do, but what we know about these spray-applied external membranes and the wrap-tight?
The wrap-tight, yeah, absolutely. It was great that we got that additional information. The biggest thing is you need to watch what these products are actually designed to do. The majority of these, well, in fact, all of the ones that I think I've come across in these spray applied membranes in the UK especially, are not permeable products. So you need to make sure that you check what the SD figure is and make sure that it is then compliant under the British Standard 5250, which is 0.6 meganewton seconds per gram or 0.12 meters for your SD. If it's not that, then it could be considered too vapor tight and you could get issues with condensation. Now, I know products like the Passive Purple that are out there and being used, great for going over blockwork, but they are vapor control layers and they are marketed as vapor control layers. And that's fine if you're then putting insulation on the outside, because then that's on the warm side of the insulation acting as a vapor check and it's not going to trap moisture. Problem is, if you use something with too high an SD value on the outside of that insulation as a waterproofing layer, you could be trapping moisture. So it's like Ian's insulation, you know, the taped foil on the insulation board, you've got the vapor control layer on the wrong side. So this is where wrap tight is totally different. And quite often people get confused thinking wrap tight is a vapor control layer. It's not, it's a vapor permeable underlay. It will allow vapor to pass out through it, yet it's airtight. So they're not comparable products. It's very difficult to get reliable vapor permeability in a sprayed product because it's very difficult to control the thickness as well. So it's really, it really is a case of check the parameters of it and make sure that, you know, it is doing what you want it to do and that you're not putting something in the wrong place. But, you know, spray is fine, but sometimes you need specialist tools for it. Whereas with the wrap tight, you don't. You can see my little child from yesterday afternoon with a corner sitting up on my shoulder there. You know, that was just done with what I had here in my living room beside me. So it would have been harder if I'd had to find a brush or a spray to put that on. So there are benefits, but it's making sure that you're not trying to put a vapor control layer in the wrong place.
Yeah, I think it's fair to say we're not experts on other manufacturers' spray applied materials. So, you know, we wouldn't be able to necessarily comment on the exact the vapor permeability claims. I can't think off the top of my head what these brands are saying. So as you say, Pam, I think it's just important that people do their own due diligence with these type of spray materials if they're using them externally, and they just check that breathability figures are clear, that they're stating that they comply. And in some circumstances, you know, I think that I can see a place for these type of materials. And we've even thought about it working maybe in conjunction with for some of our membranes would be quite a good fit. But yeah, I mean, I think, yeah, people have to take the time to make sure that they're putting the right material in the right location. And there's a place for all of these materials if they have the characteristics which fit the building envelope, I think. Okay, Ian, if I can come back to you. Carmen has asked a good one. What is the time frame for the eagerly awaited BS 5250?
That's a great question.
We're not laughing at the question. That's important. I think it's just a long time.
Sorry. It's, internally, that raises quite a lot of debate, and I'm continually asked by the board every month at the board meetings, when is the BS 525 going to be ready, Ian, because you seem to be working on it forever. So it's a really good question, and certainly you're not the first person to ask it, I can tell you. So that's why we're smiling internally here. So yeah, a good question. When is it going to be ready? It was going to be ready in August last year. It was going to be ready in September. It was going to be ready in October. The document is 160 pages, but it went out for public comment and 427 comments came back, of which the committee then have to sit down and go through every one and either accept or reject or comment on. So there's 427 comments to go through. I sit on the committee, actually chair the wall section. So we have to spend the time going through that. Now, usually that was done on Chiswick High Street, not actually on Chiswick High Street, but on a building in Chiswick, on Chiswick High Street, the BSI building. And we used to sit round the table and spend the whole day going through them. But because of the current construction details of the construction limits, we can only have the meetings on Zoom. So we have 3-hour Zoom meetings periodically, and we have had over half a dozen of those meetings already. So it's a slow process, but I think light is at the end of the tunnel. There is not a proposed next meeting. It's now over to BSI to take in all the edits, changes in drawings, etc., updating. But just at the last minute, they've looked at whether we should change the structure. So instead of going through floors, walls, and roofs, we might look at new build refurbishment type of construction. So it'll be easier for the designer to actually go through the building. They've already decided what type of building it is, whether it's refurbishment or new build, and look at all the factors to take into consideration instead of having to flick through the document. It makes a lot of sense, but it's going to put more delay. So to sum that up, I'm hoping the first quarter this year, we'll have a BS 5250 that will be better for the industry and the specifiers and all that use it to be more educated in moisture issues.
Okay, lovely. This question here, Michael has asked, I'm not 100% sure who to ask this one to, so I'm just going to put it out there. Do we have any recommendation for products behind photovoltaic sun panels in terms of the technical requirements, i.e. fire classification B1 needed and temperature resistance? Do we have much experience in them?
It's a good question. Photovoltaic panels are something that we have had a degree of experience with. Indeed, a partner of ours is actually working on some research in that very area as to what that temperature is behind the PV panels and the underlay. It's not complete. It's likely to be complete before the BS 5250 is published. But so far, the temperatures experienced are not something that would give certainly roof shield an issue, and it's quite promising, the results so far under that area. In terms of fire classification, we've not looked at what the fire classification may be in that pitched roof. Might be something that we have to take into consideration at the moment. Fire classifications don't extend to pitched roofs. So that's why we've not looked at that so far. We're just looking at the temperature that could be experienced in that area.
Okay, good. And Graham, I think I can answer this one. Graham has said, in a cavity block house, 150 mil cavity, would you advise, here we go actually, yeah, sorry. Would you advise full fill insulation or the likes of a cool therm board with air gap? Wrap-tight tape is the best solution to joint the insulation boards with. So just on the wrap-tight tape part of that question, Ian, obviously, I mean, if you were to look at the K106 Kingspan brochure, wrap-tight is named there. So we have an excellent relationship with Kingspan and other insulation manufacturers. So that, I mean, wrap-tight is the named product that you would use, and it's in their BBA, etc. Regarding the actual question between using full fill or cool therm board with an air gap, do we have any comments on that? I'm not 100% sure.
Yeah, again, I'm smiling as I'm asked that, because I'm going to say that faithful technical word, it depends. It will depend on the exposure of that site. That air gap's there for a reason. So if you're in an area that's not as exposed, if indeed you are exposed, that air gap can actually create a lot of benefits in preventing moisture, rain from outside tracking through the construction. If it's full fill, that might not be suitable in those exposed locations, because you could get wind-driven rain through the construction. Not always, but it could be possible. And similarly to why solid walls vary in depth or thickness wherever they're built in the UK. Could be thinner ones further south and in sheltered areas compared to bigger, thicker walls on the west coast of Scotland. That's for a reason. It's not because we've got lots of stone and we like to use lots of stone, well, Scotland do, but it's because of the moisture generation outside, and you're trying to stop that track through. So similarly with a cavity wall, whether you fulfill that or not will depend on the exposure ratings.
Okay, Graham said his site is on a hill. Does that help you?
Well, it helps a lot because it's more likely to be exposed. But on the top of Glenshee, local to us, that's on top of a hill, but there could be a hill in Yorkshire that might not be quite as exposed. So it's a good indication that you need to take care of the moisture, but it's a good start.
Yeah, good. Okay, I have just one final question, I think. So if anyone has any others, please post them now on the YouTube feed, or you can still email us to webinar@. Oh, there's another one coming. So I have two final questions. Pam, if I can come to you, please. This is regarding the insulation. So So should I be using airtight or air permeable underlays? And does the choice of underlay affect the insulation choice?
Yeah, okay. So a lot will depend on your airtightness strategy and the level of airtightness you want to design to. So if you're looking at particularly low levels, so say sub 3, which is the point where you need to start looking at either a passive system or an MVHR system, then using an external air barrier product like the Wrap-Tite is going to be ideal in helping you achieve it. Even more so if you're looking to get more like Passivhaus or low energy, like the sub 1, similar to what we discussed a fortnight ago in our last webinar. And they're less likely to be damaged being put externally by further trades or somebody trying to put up shelves or a kitchen unit further in the lifetime of the building. So it's going to maintain that airtightness long term. So Wrap-Tite is the perfect choice there. If you're not looking for extremely low levels, you don't want to go down the extent of an MVHR system, then it is possible to with a bit of care in your detailing, build a reasonably airtight building. It's as Ian said earlier, it's making a round hole for a round pipe, not a square hole for a round pipe, and filling in gaps and making sure that things join well together. So you may not need to use a really airtight insulation. So something like a reflector shield is probably better there because that can enhance the overall thermal performance. So it may be the case that you can actually utilise a slightly thinner stud, for example, with the reflective membranes with it than if you used otherwise. So it doesn't so much affect the choice of insulation, it might affect the thickness of the insulation you use and how well it needs to be fitted. So it's more looking at what your airtightness strategy is for your building as opposed to what type of insulation. But as Sue pointed out, there's some things like the Adapt are potentially very suitable for more permeable insulations.
Okay. Pam, Derek has also asked, when should I be airtightness testing with Wrap-Tite?
Well, most buildings will require that test at the final point of construction before handover, at which point it can be quite difficult to go in and do remediation because you've got all your linings, etc. on. So if you are designing a very low airtightness strategy, then you probably want to do testing at key points within the build so that you can actually get back in and remediate as appropriate. With an AVCL being used, so an airtight vapor control layer, you're obviously having to wait till things like your insulation and that membrane goes in, and then what happens if some other trade comes on after that and damages it. If you use Wrap-Tite externally, you've got the ability to do more intermediate testing and earlier intermediate testing so that you can assign that. And in fact, we've been involved in a project, a large leisure centre in the southwest of the UK, and it's a Passivhaus building. It's enormous, it's huge, and they're actually looking at blocking off certain areas within the construction, one of them being the swimming pool hall, and actually doing air tightness testing on that really very early on in the construction to make sure that they're on track for reaching their air changes that they're looking for.
Good, thank you very much, Pam. Okay, so final two. Sue, if I can come to you for one of them, please. Jennifer has asked, for new builds, would you recommend a hydrothermal numerical calculation from WIFI, etc., from a professional?
Okay, well, I'm probably now going to say the whole "it really depends" answer. But yes, it really does depend really on the structure that we're looking at. Glazer method is obviously, you know, completely appropriate for your lightweight structures such as your steel frame, your timber frame, etc. Heavier construction such as solid wall, for example, you would look at the hydrothermal approach for that type of structure. But yes, it really depends on your construction, on your build, and what you're proposing to actually get out of the calculation as well. But we can obviously look at both those options.
Okay, thank you. And the last question we have here from Peter. Ian, I'll ask you this because I know that you sit on a number of these British standards, so you're probably best placed to answer it. As you may be aware, roof tiles need a more robust fixing specification with roof shield. BS 5534 is suggesting a 50% greater air movement factor. Do you have any views on this?
Yeah, it's a good question. The 5534, I do sit on that committee. Again, it's still quite a robust committee, talking about different types of underlays and various applications. One of the things that came into the regulation or standard, should I say, was wind uplift. And it was always assumed that air permeable underlays wouldn't be able to take the same wind loads as airtight underlays. Which you can see the theory behind that being logical. Because if the air can pass through it can't take the same loads. But we've done tests with identical based membranes, and what we've done is change the middle layer. So the middle layer either airtight or the middle layer air open, like the roof shield. And when we've done the wind uplift calculation tests, both provided the same level of wind uplift. When I raised that in the British standard to say that I don't think that air permeable membrane should have a penalty, it was poo-pooed, would be the phrase you could use, polite phrase you could use. But they felt that they must have a penalty. So without further testing, it was decided to put in the British standard that there should be a shielding factor, which is what Peter has mentioned there, that there is a factor to take into consideration with air permeable membranes. And that is a figure that unless more testing can be done, that's the figure that they will use as a safety factor. The facts are that the British standard has moved on so much in terms of fixings that when I first started going to these standard meetings many years ago, as you said earlier, Keira, the tiles were fixed every fourth course, third or fourth course. You didn't fix every tile. Now, if you tell an apprentice roofer that just now, they would think you're mad. Now that the fixing calculations have come into consideration, most tiles are fixed, or sometimes they're fixed and clipped, irrespective of the type of underlay. So because we've increased the amount of tiles fixings, the underlay is kind of irrespective. So that 50% penalty doesn't really have a big factor on it. To me, obviously, I would say the air permeable membrane is still the safer choice from a condensation point of view, from a moisture management point of view, and what's a couple of fixings in ensuring that you've got no condensation on your roof.
Mm-hmm. Good. Okay, thank you, Ian. Right, we have come to the end of all the questions. And if I have missed any, And I do apologise, I think I've got them all today. If I have them, we will answer them via email. And likewise, if there's any questions that you wanted to ask but you didn't want them raised in this forum, then please email us, webinar@Proctor Group or reception@Proctor Group, and we'll get back to you very, very quickly. So I just want to thank everyone again for attending. We are committed to, a real course of webinars in 2021. We're conscious that people are still working at home, and that we have a relatively good audience, which are really keen to still be educated on these different topics. So we will keep delivering these. With the next one being in 2 weeks, which is Friday the 12th of February at 10 a.m. Quite a specific topic, but very interesting one. So the protection of buildings on brownfield sites. And we have a special guest, Paul Colbeck, and he is the chairman of the British Verification Council. So a very interesting topic where we'll be talking about different applications on contaminated land and mitigations and the things you can put in place along with the regulations. If you're registered today, you will receive a follow-up email. In that email, you will receive a survey. If you have time, please fill it out. We read all the feedback. I read all the feedback personally. I saw a couple of ideas coming through on the chat feed there about, if you thought about doing on-site installation videos, great idea. Okay, we couldn't do it at this moment in time due to the restrictions in place, but anything you think, it'd be fantastic to see you comment on this topic or do some research into that topic. How about this format? Any special guests you think. We've had a number of different guests on these panels and when they're willing to give up their time, which has been fantastic. So if you know of anyone who's an expertise in the areas that we operate in, let us know and we'll try and incorporate it. It really helps us if you like our video and subscribe to our YouTube channels. It'll also keep you informed about any future content that we share. And you can get your personalised CPD certificates on the webinar page on our website, so www.proctorgroup.com/webinar. And on that page, you can pretty much do anything you want in terms of contacting us, downloading product information, requesting a sample pack about the products we've discussed today, booking a meeting with one of our many technical sales team who are all based at home, desperate for Zoom meetings. They don't get Zoom fatigue, so they're keen to chat away to everyone. So please go on the website and have a look and ask for anything that you need. So thank you very much for attending. Thank you to the technical panel today. I know it's not easy answering the questions off the cuff, but a great job as always. So thanks, guys. And hopefully we will see everyone in 2 weeks on Friday the 12th of February, and have a great weekend.
Well.
Bye.
See you later.